Hello everyone, my name is Franco Pucci and I'm the STS Technical Consultant. I've been involved in the prepayment industry for over 25 years. Welcome to the STS training video series where we will explore all aspects of the STS and the STS standard. I hope you find these videos helpful. In this video, we will look at the IEC62055-52 specification. Please refer to the relevant documents for detailed descriptions. This part of the IEC62055 specifies a virtual token carrier as embodied in a direct local connection between a management device client or a point of sale and a payment meter server. It has been assigned identification code 07 by the STS Association and is generally known as VTC 07 or Virtual Token Carrier 07. It is used for serial transmission of data to and from the meter. What does it do? It specifies a client-server communication protocol that transfers STS compliant tokens from a client device or a point of sale to a payment meter server. It reads the result from the payment meter after transfer and execution of the token. It transfers management data from the client device to the payment meter. It reads management data from the payment meter and transfers the same to the client. It specifies actual encoding of the token onto a virtual token carrier, and it references a virtual register table as a logical interface to actual registers or functions. If you remember this picture from video number 7, we essentially discussed, if you look on the left, the 62055-41 section, which is essentially the point of sale and the meter application process, key management and APDUs. And then at the bottom you have the 62055-52, which is what we're discussing today, and that's the token carrier data unit and the physical layer protocol and the token carrier itself. This specification deals with the interface to the token carrier, and associated with that are meter function objects, which are subjects of companion specifications, and in there a register table interface class and a register interface class, which is defined by the STS Association. If we recall the data elements in the TCDU, we had the token data, which is the 66 bits of token data contained in the 20-digit token. You had authentication result, validation result, and token result, which are all Boolean values. And these are status indicators of the initial authentication checks, validation checks, and the meter application process result from the processing of the token. Some example physical interfaces: you have an optical port and a current loop port, which are both discussed in IEC 62056-21, and a voltage physical interface, which is specified in STS 101-1 under port types A and B. If we have a look at the transmission format, you have a start bit, then you have essentially 7 data bits going from bit 0 to bit 6. You have a parity bit and a stop bit at the end. The transmission is a synchronous data transmission of duplex. It comprises one start bit, 7 data bits, 1 even parity bit, and a stop bit as shown above. The baud rate is 2400 baud, and there is no baud rate negotiation. Let's have a look at some of the supported commands. You have an ID request message, which is essentially is used to request identification data from the server, and that's a / question mark, exclamation mark, carriage return, and line feed. Underneath that you will have the hexadecimal equivalents. You have an ID response message in response to the ID request message, which essentially has a / and M, or the literal ASCII M, indicating that a manufacturer code data for 4-digit manufacturer codes. You have 2 characters of manufacturer code in this specification, and you have the 4-digit manufacturer codes, which will be specified in STS 202-4. Unfortunately, this spec is a bit old, therefore it only allowed for 2 digits of manufacturer codes. And then right at the end you have a software version which is 4 digits. The read command message is another one which reads a client data set from the register and the server. It has an SOH or start of header, and R, which means it's a read command, the STX, the register ID. Register ID is a number from 0 to FFFF or 0 to 65535. That's how many registers can be supported theoretically. You have the data length from 0 to 10 or 0 to A in hex, end of text, and a binary coded checksum. The data message, the server responds to a read command with a data message response, and that is an STX. Then you have 2 delimiters. You have a left bracket or opening bracket, which is a 028. You have the closing bracket, which is a 029, and encapsulated in those 2 brackets is the data itself, which has been sent back by the server, and that's in the range 0 to 9 or A to F. Then you have an ETX and a BCC. Write command message, where the client writes a data set to a register in the server. There you have an SOH or start of header once again. You have a W indicating that it's a write command, start of text, then a register ID, which is a 4-digit register identifier. You can see clause 6.8 for the registers. Then you have the start and end delimiters. You have the data characters, which once again are from 0 to 9 or A to F, and then ETX and BCC as before. The break command. This command essentially cancels all previous messages that have not been executed by the server. So the moment the server sees this, it cancels anything else it was doing. That's an SOH, a B, which is 0x42, in hexadecimal, ETX and BCC. And then last but not least, you have an acknowledge or not acknowledge message that can come back from the meter. The server protocol flow diagram, let's have a look at how this works. You have a token carrier on the left flowing through to the connector of the token carrier, the TCDU or token carrier data unit. That connection is covered by the physical layer, IEC62055-52 in this case. Then from TCDU to APDU, that is covered by the application layer, or IEC62055-41, which has been discussed in other videos. And then you get through from the APDU to the meter application process. So what happens, let's say you have a write command coming in. The write command is processed, and at this point you can send back an ACK or a NACK. It goes through to the TCDU. The token is then decrypted, and the token data is extracted from there. At this point you get an authentication result and a validation result that are generated, and they can be sent back to the TCDU, but at the moment they're just held there. They're also sent forward to the APDU. APDU then extracts the token, and the meter application processes this token, and it will send back a token result, as well as checking that the authentication and validation results were in fact okay, going back in. The token can then be erased at this point. For example, if you have a token carrier type 01 or a MAG card, then the token would be erased at this point if it has been accepted. If you have a token lockout, the token lockout can then come into effect. For example, if the authentication or validation results show that it's an invalid token, the token lockout then could come into effect at this point in time. If there is no token lockout, then of course the token result would go back to the point of sale. A read command, if that's issued, what happens is the read command is processed, and you get either data back from the server or a not acknowledge. If we continue, you have an ID request as another command. The ID request can be processed, and you either get an ID response coming back or a not acknowledge. Similarly, with a break command, you get the break command that's been processed and an ACK or a NACK. and for any undefined command you would get back a NAC because the command is undefined. The client may send messages in any sequence, and the server must process each message in the order that they are received, except for the break command, which is processed immediately. A communication session constitutes one message pair initiated as a request from the client and ending with a response from the server. For a full list of the message processing function, please have a look at the specification itself. Token lockout, we'll talk briefly about that. The token lockout only affects tokens entered via the virtual token carrier interface, and the reason for that is because the acceptance rate on, for example, a keypad is typically 10 to 15 seconds, which is slow enough. But through a virtual token carrier, you can send many tokens rapidly, for example, if you're trying to defraud the system and work out what the beta key is. Shortcodes are not treated as tokens. In other words, the token lockout does not apply to shortcodes. The tokens must be locked out for a period of time after each rejection, and the maximum lockout time of at least 60 to 120 seconds must be reached after 10 successive token rejections. Token lockout must be reset after the acceptance of a class 0 or class 2 tokens. So the moment you accept one of those two classes of tokens, you can actually restart the whole token function and reset it. The remaining lockout time must be available by reading the appropriate register in the server. The STSA has defined certain registers, and you can see them here. 2000, which is the protocol version, 2001, which is the table ID that you're currently using, 2002 is the server status, and then software version, binary token entry, token status, and token lockout time remaining. You can see STS 201-1 for all of those definitions. But please refer to the 52 and STS 201-1 documents for details on the implementation of the specification and a full list of register IDs. This brings us to the end of this part of the video series. I hope you found this video helpful, and I hope you will join us for the rest of the series. Goodbye and see you again soon.